Hello everyone! What happens if we try to flood Venus? I will launch giant volumes of water, from 5 to 500 quintillion liters, and we'll find out what Venus will eventually turn into, all using the Universe Sandbox simulator. Let's go! Well, you can see that the object is already on a collision course with Venus. Let me hide the atmosphere clouds. You'll see everything more like this. We see the water sphere and Venus itself with a molten surface. Well, again, just like in the previous video with Mars, where I also flooded it, I disabled gas laws for this object so that absolutely all the water here reaches Venus and nothing is lost. And this object contains 5 quintillion liters of water. Here, please, is this mark. Well, if you translate this number in terms of Earth's oceans, it turns out there's not even 1% here. I think we can enable the cloud display. Well guys, the most interesting part is about to begin. Let's watch 10 seconds pass per second, but as I understand, the object has started to collide. It has begun. Ah, look, it's starting to collide. The tearing was happening there, all this was going on, but not too quickly. It managed to tear apart there because the object is already flying in, and we see a lot of water starting to spread from the epicenter of the collision. The flooding of Venus, so to speak, has begun. I'll speed up time a little more. Oh, all these gases are so blinding. I want to focus and look more closely and hide the gases. They were hidden. Well, alright. There we go. Oh, what has this liquid turned into? It has somehow changed its appearance, but the flooding continues. Alright. Well, here, you see, there is such a large trace from the collision. That's not very good, and basically Venus flooded to about this level. Here, of course, I heated it to 3950 degrees Celsius at the collision site. In general, I'm speeding up time, letting everything cool down, and we'll see what happens next. So, about 1 month passes per second, and as we can see, all this water unfortunately starts to evaporate. I'll turn on the atmosphere clouds for display. Oh. I understand that it will become even harsher here now in terms of atmospheric pressure. Well, as we can see, all the water has completely evaporated. What will the final temperature be? So as we can see, the maximum is 577 and the average is 479. It became slightly hotter than it was before on Venus. In terms of the atmosphere, as we can see, the pressure became 135 atmospheres, which means it increased, roughly speaking, by 40 atmospheres. It became, as I said, even harsher. If we look closely at the composition of the atmosphere, we see that all this water has gone into the atmosphere and makes up 13 Earth atmospheres. So guys, I decided to repeat this experiment. Again, we will have 5 quintillion liters of water here, but this time I have turned off the heating from collisions. Simply because of that collision, it most likely causes an effect that quickly evaporates the water. But if there is no heating and all the water just pours into Venus like this, that's it. Let's see how it turns out in the end. Maybe this water will remain. Look, the object fell, the water transformed. And do you know why it transformed? Because it mixes with carbon dioxide. I'll show you later. Let's speed up time and see what happens in the end if we turn off the heating from collision. Speeding up? No. You see, everything disappeared very quickly like that. I thought it would be something more interesting. Oh well. This is really strange. Even the pressure didn't change this time. Let's see. Maybe an object that already contains 50 quintillion liters of water. There you go, this value is restored, and this time let's disable the heating from collisions, and we also need to eliminate gas loss. All the water should reach the surface of Venus. A nice eclipse is created on Venus by this object, but I will still hide the atmosphere from the display. Well, let's see what the result will be. The collision begins. Well, intriguing. This time, there is already 10 times more water than in the first experiment. The object entered completely, without causing any harm to Venus. And as we can see, a nice body of water is spreading here, speeding up time. Let's observe the further consequences. So we see many bodies of water are forming across the surface of Venus. Fragments that flew out after the collision fall onto the surface of Venus and, so to speak, spread the water. But look, for some reason the water is evaporating back. Just very quickly, it lingered for a short time, unfortunately, and something similar happened. Like last time when I turned off the heating from collisions. Well damn, this is all boring. Well damn, why is it like this? Okay, let's speed up time even more. Focusing on the surface. Well, all these bodies of water that remained have also disappeared. Well, this time at least the pressure is higher, 103 atmospheres. But I understand, guys, that it's better not to turn off this heating from collisions. It's more interesting with it. Now the heating from collisions is enabled. Let's see what the outcome will be in this scenario. The object has begun its collision. So, the heating has started, and you see the water somehow spreads better this way. Maybe the simulator works more adequately with these parameters, speeding up time. The checks up. Oh, how these flying fragments are blinding. A tsunami like this is spreading across the surface of Venus, and here it stopped and starts mixing with carbon dioxide. Let me show you, before all the water leaves the surface, how it mixes with carbon dioxide. Look, here's what happens. There's not only liquid carbon dioxide, but also liquid nitrogen and liquid sulfur dioxide, and water. Mainly there's carbon dioxide and water here. Even the concentration of liquid carbon dioxide is increasing. Currently in the atmosphere we have a lot of carbon dioxide in water, already 30 Earth atmospheres, still it all starts to evaporate and the level rises. I will speed up time and you will see that. Yes, 31 Earth atmospheres. For now the water is holding, but it is slowly starting to evaporate. Let me focus and show you everything in more detail. Here's the situation for now. If I speed up time further, unfortunately, the water from the oceans evaporates and everything goes into the atmosphere. Liquid cannot remain on the surface of Venus for long due to the enormous temperature. Although, as we know, if the surface pressure is high, liquid water can exist because the boiling point of water is higher in this case. But here, most likely, even 120 atmospheres, which are present here, are not enough. In general, we speed up time and watch how all this disappears from Venus. Well, at least it could be at the poles. Well, most likely, water needs to be distributed and then it would get there. And this is how Venus looks with a new atmosphere. It has become even denser and the pressure eventually formed at 124 atmospheres. Well, I think the most interesting experiment will be what happens if an object that already contains 500 quintillion liters of water, here, this value, collides with Venus. Will it be able to have any impact? By the way, if you convert 500 quintillion liters of water into Earth's oceans, it turns out to be 35% of one of Earth's oceans. And when I set this value, we see that the radius of this object has slightly increased. So let's see what Venus will turn into after this infusion of water. 500 quintillion, I repeat, liters of water in that object. The collision begins. The water spreads. Well, I would like it to linger. Really would. The object has completely fallen. Now let's speed up time, see? So far so good. An active tsunami rushes through. I'll slow down time. I want to show you. Let's lower it here. And that's how it all spreads. And let the atmosphere be displayed as well. And this is how everything looks on the surface here. And now a little to the side. Oh, right here, the water reaches this place and we see how it spreads. Well, it's epic, a dense atmosphere, nothing is visible, but we see this spectacle, returning to space and hiding the atmosphere from view, speeding up time again. Well, this time the water spreads significantly there. You could say it covered half the planet. I'll turn on the flashlight. Let's look from the dark side. Well, from this part, no, the water didn't reach. Yes, it looks epic. Here the water doesn't mix much with carbon dioxide and in principle it looks normal. But these fragments still fall back and create what seem like temporary islands. If you speed up time, then most likely it will be the same again. Evaporation. But here you see the water has already reached the poles. Perhaps the poles will have water. I really hope for that. You know, this already looks nice. I hope everything works out. If you turn on the atmosphere display, then of course everything is like this. Clear. Let's hide the atmosphere again. Well, we can already see that the pressure is 166 atmospheres and the greenhouse effect is 10,000 degrees. Oh my. Well, if this part cools down, then I think everything will stabilize. In general, I'll focus on the surface, speed up time, and let this maximum temperature drop below 1000 degrees. And then everything will be clear. Oh, what's happening here already? Well, yes. You see, all this water is slowly starting to leave the surface again. Oh, but I hope it won't leave here, at the poles. You know what I'll do? I'll distribute the water evenly. Oh, now the poles are flooded. Maybe the water will stay there. But now Venus looks so interesting, you see. Here we have ice, here it's molten. In short, Some kind of nonsense. Well, it really looks like ice, although there are no negative temperatures here. I don't know what it is. Vegetation isn't appearing anywhere, but that's understandable. Let's speed it up more. Let it be. Oh, the water disappeared very quickly, and unfortunately even from the poles. It is what it is, guys. Well, let me try launching such an object again. I'll turn off the heating from collisions this time. Maybe something more interesting will happen. Alright guys, it's ready. The heating from collisions is turned off. The object is relaunched. Let's see if anything changes. I really hope so. I want at least some liquid to remain at the poles. Really. If the temperature is lower there, it might stay because the pressure will hold that water. Okay, excellent. The object has fallen. Speeding up time. Well, please spread water. So far not bad. Alright, come on, don't go away, spread out please. But if it doesn't reach the poles, it won't make any difference. Well, it seems all the fragments have fallen, so I can now spread the water evenly across the surface. I'll do it like that on purpose now. Wow. That's amazing. And now let's look at the planet from all sides. Yes, the water has spread nicely. True, but for some reason this part is all in ice again. But here it looks good. And now I want the water to stay at the poles. It's clear that everything will leave the equator, but I want the water to remain at the poles. I'll focus, let's take a closer look. So more, speed up. Okay, the water is evaporating here, I see. Why are you evaporating at the poles too? Oh, come on. I tested it off camera. I managed to make it so that the water didn't evaporate from the poles during some experiment. But here, during the video recording, for some reason it didn't happen. But you see, the minimum temperature is 250 degrees. And we got, as you can see, 264 atmospheres of pressure. Incredible. But I want to show you under what conditions there can be water at the poles at least. We need to lower the temperature a little bit. Let's increase the average albedo even more. Let's set it to just 0.98. If the temperature becomes around 100 degrees Celsius at the poles, water can appear there. I'll speed up time. Oh, the temperature has really dropped here. Wow, even zeros. Now theoretically water should fall from the atmosphere as rain and flood a little. Here, I set it to a month a second. Well, you see, we have plenty of water in Earth's atmosphere. 195 atmospheres. Let's freeze all this water from the atmosphere. Oh, this is certainly epic. Everything is suddenly evaporating back into the atmosphere. And we see that liquid is forming at the poles. Anyway, I'll wait and then show you the final result. In general, guys, it turned out even more interesting than I expected. The water isn't evaporating across the entire planet. Here, half a year passes in a second and everything is stable, the temperature is stable. You can see for yourself, everything is very good. There is water at the poles, and in the end, here on the surface of this Venus, the pressure is 133 atmospheres, the greenhouse effect is 320 degrees, and the average temperature is 163 degrees Celsius. There is also a decent amount of water, almost 20% of Earth's oceans, and the water in the atmosphere is 67 Earth atmospheres. The other elements are basically the same as Venus originally had. Well, the simulator shows that the probability of life on Venus is 0.18%. If you also display the atmosphere, Venus looks like this, and like this under sunlight. Well guys, that's how we poured entire oceans onto Venus, and it still remained an inhospitable ball of hell, essentially. Well, a planet with character it seems. But the experiment in principle was successful, and it was epic. Write in the comments whether to continue this series. Also don't forget to like. Thank you very much for watching, and see you again in the universe.